Welcome back. What a week this is. We can mercifully wrap up Bayes today, hopefully. I will tell you, Ahmed, I have your auto correlations. Akyung, I have your standardized coefficients. Not only do I have the standardized coefficients, I have the Bayesian version, which is even better. So we'll get to that in just a bit. But I wanted to start with sort of some, normal housekeeping work. As you saw today, we had our chapter five quiz was due yesterday. Today, just a few minutes ago, you should see an icon. This should be homework four, not five. Of course, a typo. Come on, Jonathan. It's one problem. It's Bayes. It's take the last ML problem and put it in Bayes. I will talk about it when we get through today's class. I'll give you some hints on where to start. Okay. So it's JAGS code. I know not everybody wants to do JAGS code, or not everybody feels fully prepared, and I understand that. So I'm willing to work with you on this. If you get started, I'll be happy to help. I'm anticipating having emails with you to get through it, okay? And at the very least, at the very end of this, if you ever have to go back to JAGS, at least you have a place to start. That's what I'm hoping. But it's only one. It's not multiple models, just one. That's number one. Number two, I mentioned don't read, or you could skim chapter six. I will talk about chapter six, and actually, I'm going to talk about it. I think it's more of a technical topic. So I'm going to show you the paper that led off everything, and really the result, which is this line and these lines right here, which is really cool. But then I'm going to try to put it in context. I don't have slides on this, but I'm going to just talk context why I'm kind of like not cool with chapter six a whole lot. I guess I can see it from a deeply theoretical perspective. From a practical perspective, I think it doesn't matter as much. So that's why I'm sort of like move those out. And then next week we will do the best part, the part that may be the easiest for you to do missing data with, multiple imputation, right? We will talk about how we do multiple imputation from chapter seven. There's a chapter seven quiz, so I'll ask you to read chapter seven, answer a few questions about it this week. That'll be due next Tuesday. And then we will have a lecture on multiple imputations. I will likely use the package mice, which you've already downloaded as part of your homework a couple times ago. What you will see is multiple imputation is great because for every single data set you get, there is no missing data. The problem is sort of what do you do if you have 100 new data sets and you have 100 analyses? What do you do after that? So we're going to talk about that as well too. And nice thing to know, if you use Lavon for any of your analyses, there are options in Lavon or packages that use Lavon that integrate all the things to do afterwards with the multiple imputation as well. So how about that? Convenient. So we're going through all the hard parts because some of you might at some point need it, some of those, but we're moving forward to anything to something I think next week will be much more pragmatic and practical. Do you have any questions for me about anything that we've talked about? Nothing. It's like, is it no question or is it missing data? So I got to just ask for. I'm sorry. Like this time of year, I don't know about you. Like Lisa comes home and she tells me, "Oh, class, nobody wants to say anything. Nobody wants to do anything." And I'm like, "Oh, you just need to joke more." Yeah, clearly, because I have all the answers, right? No, I'm trying at least. I'm trying to at least engage you. This material is not easy, and it's my time for through. It's hard. Yes. Yeah, absolutely. Yes. 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 Yeah, that part was very confusing. It, if That's a great question. His derivation works on multivariate distributions, right? So if you have jointly, like he had an example with y and an x together, and he's like, oh, look, if we do the Bayes process, then there's a part of y, a part of x goes into what happens. But I think it's more from a more of a technical perspective in some respects. Look, the process of Gibbs sampling, the process of Bayesian statistics, or Metropolis Hastings, all incorporates everything he said into the algorithm automatically, right? And so he's talking about it, and I found that hard to place as well too. That's why I was sort of approached chapter 5 a little bit slowly. I didn't find it a practical like demonstration because there's nothing you can do with it except for that one example. You might be able to take that result and try to code it, but a general sense of what you're doing is more limited. So I think from that sense, to me, the multivariate data is no different than the univariate data in some respects, except for if you're trying to code it yourself and you have a specific instance of a multivariate distribution, then you may need there may be a shortcut that you can get to get a more accurate sampling distribution, like in a Gibbs sampling sense. But that's not always applicable and not always easy to do. So I hope that helps a little bit. Long story short, I read it and I thought, good example, theoretical example, but there's nothing practical, I think, that really comes from it. Okay? Does that help? Great. Other questions? No questions. Shall we start with R? Yes, I'm already asking this. Come on, Jonathan, get your act together. Let's go. By the way, I've been talking to my kid a lot. That's what he always says. And I always have to reply as an old man, hey, where are we going? Because that seems to what a lot of the folks on, believe, video game YouTube like to scream every time. Let's go, let's go, let's go. Yeah. Where are we going? All right. Let's get started. Let's start with autocorrelations first. And then we'll talk about standardized coefficients, and then we'll finish the example here. In reality, we may not have a full lecture today, but I didn't want to break up multiple imputation into multiple parts. So we will go through this. We'll talk about homework at the very end, and we'll see how it goes. Okay? Of course, every time I say that, what happens? It's not going to be a full lecture today, and it takes a full time. So just ignore what you just said. But if you get out early, is anybody going to complain? I'll take your complaints. I will. I'll apologize. How's that sound? Okay. I was told once education is the one product that the consumer really wants less of, like when they're taking it. So there you have it. That's not it. Okay. Let me get to. So before we had run JAGS. We had to run. I wanted to run this multivariate model, and it didn't quite work based on our data. So I created because we had a multivariate distribution and we had like multivariate normal. And JAGS is like, wait, you can't have like if you have two variables as part of a bivariate or multivariate normal, one can't be missing, right? You can't miss one and still use it. So JAGS, ugh, kind of a problem. So instead of that, I just made the complete data just to show you how it worked. And I'll just use the complete data to describe what we have. The reality of it is what happens is when JAGS runs, it spits back this object. And this object, model 101B JAGS samples, is an interesting thing. You have to sort of parse it a bit to figure out where everything that you really want is, right? If you just use the name of it, you get this sort of summary statistic output. But if you go to investigate it more, it's an RJAGS object, which is an odd thing to think about. But then if you look into like what its elements are, there's an element of it called bugs output. This is how old all this stuff is. Bugs is a program from the 90s that became WinBugs in the early 2000s. And probably you may have heard of WinBugs before. OpenBugs is, I think, another version of it. It was the original Bayesian updating by Gibbs sampling. That's why it's called Bugs. And it led into JAGS. In fact, if you read the JAGS manual, it says not unlike Bugs, right? So they're both open source. So anyway, JAGS is sort of the maintained version of what Bugs was. If you go in there, then you start to see the Bugs output. And in here is where you'll find all of your samples. So there's no real easy way to go and take this RJAGS object and get your output to give you autocorrelations. I'm telling you all this because there may be other things that you need to do in Bayes with a JAGS piece of output, so I'm sort of digesting it. So basically what I do is this. I go and I find bugs output, and in there's a series of arrays that have the chain. So we have Sims array, we have Sims list, and we have Sims matrix. All of those has the same values displayed in a different way. Okay. Sims array, if we take that, if I ask for the dimension of it, what you'll see is there's 5,000 of the first dimension, 4 of the second, and 7 of the third. Now, with a little bit of math, we can do some detective work. What we see is there's 4 chains. Hey, that's got to be the second dimension. So what this array has is it's a 3-dimensional array. Have you ever worked with a 3-dimensional array in R? A data frame is 2 dimensions, right? A 3-dimensional array, it just has another dimension to it. If I take this Sims array object, like I would with a data frame, I can actually select one of those middle ground areas, one of those chains itself. And what we'll see when I do that, why did you just do that? There, is I get basically what looks like a data frame out of it. So let me just show you this. So one chain's object looks like this, right? We have each of the parameters that we saved in the model right here as a column. The deviance always shows up. That's your clue that JAGS is, this is from JAGS. Deviance shows up there, right? And there are 5,000 entries. So we're pretty sure that this is one complete Markov chain from JAGS, right? So that's where to start. When you couple that knowledge with, so Sims array basically takes your Markov chains and puts them into this 3-dimensional object where the first dimension is which iteration number, the second dimension is which chain number, and the third dimension is which parameter. That's convenient because now, remember, a lot of our output statistics, like the Gelman and Rubin R hat, rely on between versus within chain comparisons. So this is what will give you those comparisons potentially for each of the 7 parameters. I just wanted to say a moment about the other objects as well in the interest of trying to teach you a little bit more about JAGS. Notwithstanding, you may not use JAGS, but just in case, in here, the other values were Sims matrix and Sims list. So if we do Sims matrix and we look at the dimension of it, it's 20,000 by 7. So let's do some math here. We saw in our Sims array, there were 5,000 iterations per chain. This disentangles every chain and lumps them together into one big matrix. So this type of object would be good if you wanted to plot the histogram, right, of your posterior distribution or the density of your posterior distribution. In fact, oh boy. Nope, that didn't do it. Let's take the first parameter. There we go. That is, I think, the correlation parameter. Is that the correlation parameter? I don't know what parameter that was. Not sure what the first one is. It is correlation. What? No. Oh, I didn't normalize the density. But this is the density. Ignore the y-axis. I didn't actually remove this and make it more on the scale of what you have. But this is our smooth histogram of that density across all the distributions, all the chains, right? So when we look at convergence, if we say the correlation converged, that's going to be the density that we draw our EAP or our parameter estimates and standard deviations from. Okay? So Sims array is good for output diagnostics. Sims matrix is good for reporting and plotting and all the other stuff. Sims list, I think, is pretty much useless, but let me show it. It's not useless. I shouldn't say that. I use it less. How's that? You want the real unfiltered version, or do you want just like the like you know talking to the boss version? The real unfiltered version is like, yeah, this is crap. But um, in a list in R, of course, we have to talk about it with length. So what we have here is an array of length 7. So that should tell us what each element in the array and the list is one of the parameters saved, right? And so if I look at it, and I just want to look at the very first parameter, that is a 20,000 a matrix with 20,000 rows and 1 column. So that's the same, basically that's the first column of sims.matrix is what that is. So it's sort of separating each parameter into an element of the list. Okay, all that's great. However, what we need to calculate autocorrelation, which is what started this whole thing, is we need something called an MCMC list object. So there's a package that R to JAGS uses, which honestly I've been using since probably 2001. That's how old I am and how old it is, right? It actually goes to the 1990s. One of our former stats professors here on campus is a co-author of it. She's famous. Kate Cowles is her name. If you go to this code, it's called CODA is the package. And CODA basically is built, it's called convergence diagnostics or something like that. Anyway, um, we need to format our MCMC as a list. And that's what I do right here. I take our array, actually, in this case, I'm trying to determine, yes, the Sims array again was our three-dimensional object. So for every chain in the array, I'm going to output a formatted version of that um, matrix where all the samples, all the iterations, bless you, of every parameter is saved. And I'm going to save that as something called an MCMC object. If we save it as an MCMC object, then Coda runs on it. That's the main thing. But I have more than one of them, so I create a list. This lapply function in R always returns a list. If you're not used to R, it sucks. It's the worst function in the world. But lapply sort of loops through every element here and applies the function that you define to it, outputs it as a list, and sure enough, there's a function from Coda called mcmc.list that makes it an MCMC list. What that is an object where every element is one of the chains of your MCMC. So you build that. With me? Probably not. That's okay. Come back to my code someday. Um, I'm not saying it's not because of you. It's probably because of me. So when I say that, let me help. Um, Now we can take chain list and do autocorrelation with it. So for instance, here, if I use the Coda package autocorrelation, and let me just make it where you can display a little bit better, we see the following, right? These are the autocorrelations. Basically, every chain, by the way, will have an autocorrelation. How we find the autocorrelation is simple, relatively speaking. We have 5,000 iterations, right? We want to know the correlation of one iteration with the next. So we create a data frame where we take 5,000 iterations, 1 through 5,000. We copy that, and we start that on column or row 2. So now our data frame has a bit of missing data for the very first and the last element, and everything else is complete. The correlation of that is our autocorrelation. Does that make sense? Like it's lag 1 correlation. So that means every chain will have every Markov chain will have its own value of autocorrelation, and autocore.diag will give you the average across all 4 chains. I should note that that is different than if you just do autocore, which will give you the autocorrelation within each chain, right? So the within chain autocorrelation doesn't help us as much because we want the between chain autocorrelation because that's how we're going to report our results. So this tells us at lag 1, the autocorrelation for each of our parameters. Ignore deviance. That's sort of a weird one that's always going to be there. This is going to tell us our correlation for this model is very small at lag 1, right? So we don't need to worry about thinning our chain or running it extra long. The other thing it will do is it will plot a autocorrelation graphic to help you diagnose if the autocorrelations are high. You would just, what you see here is nothing because they're all very close to 1, right? Now, what does it mean to have a high autocorrelation? Think of it this way. The correlation at lag 1 indicates how correlated the next value in the chain is. Now remember this process of sampling, depending on the algorithm used, if it uses, and we don't know which algorithm is, we actually have to dig deep into that bugs object to figure out which algorithm is being used. But remember Metropolis Hastings, remember that algorithm? It did something called rejection sampling, right? Where it would propose values, and if those values were too far away from the center of the distribution, they get rejected. Well, that means at time 1, and then if we propose values for time 2, if they're rejected, they're the same values from time 1. So Metropolis Hastings often has a longer or a higher autocorrelation because its proposal values may not be very efficient, right? Gibbs sampling I believe this is probably a Gibbs sampling algorithm the way it's implemented. It has usually can be less autocorrelation, but depending on the nested structure of your model, like which blocks of parameters are being sampled when, it can be high as well too. When do you get concerned about autocorrelation? Well, how would you like to know? Uh, in certain ways, right? Ahmed, I think you pointed out at the end of one of the pieces of output last week. If we look at, I don't want that. I don't want this. We look at our ineffective sample size, right? Our correlation was 2,400. Why that's important is think of it this way: we're using summary statistics of our sample of these drawn parameter values. So whatever you remember from basic statistics, literally, about what's a good sample size to have confidence, that's what you want this ineffective to be. So for the mean, a mean out of 2,400 observations, probably going to be a very good estimate, right? A standard deviation, a little bit harder. 2,400 observations, though, should be plenty. The part where this ineffective really matters is in one of what we call the order statistics, right? If you're really concerned about a posterior, sometimes I didn't cover it in this class, but if you take some other Bayesian classes or maybe go through my slides, we talked about something called the posterior predictive p-value, right? Where we're talking about the number of samples that are above or below some threshold. In our case, we may be concerned about the correlation being above zero, right? Now that's a count where that zero value is at one of the tails of the distribution, right? So sampling a tail of a distribution is really unreliable with small sample sizes. So you'd really want a larger effective chain for that reason as well too. But generally speaking, autocorrelation is not, it's a problem of efficiency, right? The chain just runs, it takes longer, you have to run it longer. It's not a problem of non-convergence necessarily. And when you get into making algorithms run faster, there have been entire multi-million dollar research programs developing algorithms to make things go much more efficient. But if you have a little bit of time, particularly for the models we're doing, should be okay for it. Does that answer your question about autocorrelation? Did that overkill the autocorrelation? I'm trying my best to teach something. All right, something. There we go. So we can do that. I'm going to do that with the rest here. Okay, that was question one from last week that was unanswered. Agung, you asked it. I can't even talk. You asked about standardized regression coefficients and how we compute those in JAGS, right? So let's go a little bit further into the standardized regression coefficient. I am going to move to, let's see here. Actually, yeah, I did change this. Where did it? There we go. Okay, so I'm going to move down to model 2B. This is the model where we have our performance and use variable being predicted by the female variable and the CC10 variable. And what we have to think about is, number one, what is a standardized coefficient? Right? A standardized coefficient is a basically unitless measure of regression, kind of like a correlation, right? When you learn when you learned about standardized coefficients, what did you learn? What were their how did you go and get standardized coefficients back in the day? Does anybody remember? Neither do I. It's part of the reason I had to wait till this week. I had to go look it up. The advice is this: standardize your data and then run the model. That's one way. So, like running a model on z-scores. Okay, that's one way. Another way would be to try to take the coefficient, realize the units of the coefficient, and make the units cancel. Right? So, what is a regression coefficient? What's the units of it? Right? If I have, here, let me run this analysis real quick. I have a regression coefficient here. It is the use variable being predicted by CC10 and it's 0.162. What does that mean? 0.162. That's right. So for every one, whenever CC10 goes up one, and that's of the scale of CC10, use goes up one in use units, the units of those, right? Nothing other. A standardized coefficient works a little bit differently. Anybody want to guess as to what, how, if this were a standardized coefficient, how we would interpret it? That's right. So for every standard deviation increase in the predictor, this would be the standard deviation increase in the outcome. All right. So now let's think about how we derive that. CC10. So why? So one of the, depending on how you look at it, one of the best things or one of the worst things about Bayes is you have to create your own effects, right? And if I wanted to standardize a coefficient, I could do so by taking my current coefficient, multiplying it by the standard deviation of that coefficient, and dividing it by the standard deviation of the outcome, right? Why is that the case? Well, let's think of it this way. What we just described, let's stay with the was it use CC10? Let's stay there. Use CC10. Its metric is uh, use units use per unit of CC10, right? So if we want to, if what happens when we multiply the square root of CC10 is we're effectively removing the unit of CC10 from the measure. You remember in chemistry there were these. Uh, so if you saw my high school transcript, okay, I failed chemistry. I did, but I took it again. I took it twice in college, and I think I at least did enough to get an A. It was community college, but it built me. So that's who I am. All right. There's a place called stoichiometry where you had to cancel units. Do you remember that? Moles of this, liters of that, whatever. That's basically what we're doing with standardized coefficients, right? So we need to remove the units of CC10 and we need to remove the units of use. And what we're left with then is standardized on the standard metric itself. So what we need then is to understand that our measure of a unit would be the standard deviation itself, right? That is a metric that we go by. So when we multiply our coefficient, that is units of use by units of 10, by something that's units of 10 and units of use, units of CC10 units of use, we end up removing each of those. And what we're left with is a standardized coefficient. So that's the concept first. How are we doing with all of that? You can go into Levon and check the math on this. Yes, that's right. Well, if you think about the covariance, like if we go back to that first model where we had the covariance, covariance is on units of x times units of y. To get a correlation, we divide by the standard deviation of x times the standard deviation of y, removing the two sets of units, leaving it unitless, right? So that to me described or unitless or talking about standardized unit. Basically, the unit is one for each. Same thing is happening here. Same idea. It's just the term we're multiplying, which is a coefficient, have different units than a covariance, although we could get a covariance if we wanted to out of this, right? Yeah. Yes. Ah, good question. Good question. In part to me, because um, I guess we could do that. I wonder if we could do that. I haven't thought about it that way before. Let me do a quick little math here. Uh, hmm, it's possible. It may be the case. Yeah, potentially. I think you may be able to do that, but I may be wrong about that for right now. And I'm not entirely sure there. Let me go with my approach here, which is for every iteration of the chain, we have use CC10 as a model parameter. So we actually have the regular unstandardized coefficient. We could go and build a corresponding standardized coefficient at that specific Markov chain. And I actually think this is where it will differ from your solution a bit. Because to do that, what we would need is basically the standard deviation. I have the square root of the variance of CC10 over the square root of the variance of use to do that. Now, here's where the fun begins. And this is the difference between Bayesian and frequentist. And this is another reason why I think the result will be slightly different. Um, the fun begins in that, in a frequentist sense, and believe me, if you go to ChatGPT, ChatGPT will suggest this for you too. To get these numbers, it says, "Oh, just import these into JAGS." It told me that. I was like, "Hey, how would you do it?" Yeah, why not? But that's a point estimate, and we're a Bayesian algorithm. So there's a mismatch between fully Bayes ideas and that point estimate, which may or may not be an MLE that we're using to standardize. So instead, I wanted to go and we can actually create versions of the variance that we're interested in, right? So for instance, in variance of CC10, we go back to our CC10 model. The variance of it is actually being estimated because we're not predicting CC10 with anything. This tau is 1 over the variance of CC10, so we can actually just calculate a variance component for it. Now, think about it. Every step of the chain, this thing's getting sampled, meaning we get this variance being sampled on its own, so we can use that value to standardize our coefficient, right? For use, it's a little more complicated. Use has a model. This is its model for the mean, and then it has a variance to it. And here, our model for the mean, if we actually go and break down, remember that algebra of expectations lecture? That's what we got to do here too. If we wanted to see what's the variance of use, it would be the variance of each of these terms plus that variance plus potentially any covariance between them, right? Variance calculation. Well, the variance of a concept is 0, so that it goes away. The variance of use female is the parameter, but what we would get is this thing squared times the variance of female itself. Same thing here. This coefficient squared times the variance of CC10, and then plus tau use. Now, when we add two things together, the covariance of the sum technically is the variance of one plus the variance of other plus 2 times the covariance. But if you go back to our model for female and for CC10, they're uncorrelated. So the covariance must be 0. So in this case, we keep the covariance at 0. Therefore, we can actually create our standardized coefficient in the chain itself from that premise, understanding that what we have is the standard deviation of the variance of CC10 divided by the standard deviation of the square root of the variance of use, right there. And there's your standardized coefficient. How does that sound? Now, this will be different than if you are doing this same process. If you're looking at the output of Lavon and you have the standardized coefficient on the right, this number may be slightly different than that number. But the other cool thing about this is now we have a posterior distribution on our standardized coefficient, right? And that posterior distribution may or may not depend upon, or the influence, how much uncertainty we have in estimating the variance of these two quantities is going to affect that posterior distribution itself. But the cool thing to me about this is now we can, here, let me see if I can plot it real quick. Of course, I'm not plotting here, but I make these lectures. I'm like, I'm just not going to plot it. And then I get into class. I'm like, why did I think I wasn't going to plot it? So let me just take a moment to plot this and show you the posterior distribution of it. Oh, of course, that looks great. Ah, boy. All right, you know what I'm going to do instead? I'm going to just look at the density of my one of my standardized coefficients here. There we go. That's the density for our standardized coefficient for CC10. And if you want to compare that to the density for our non-standardized coefficient, you'll see the shape of it, the shape is not that different, right? And the only thing that changes between this is the x-axis, so the values themselves. But there you have it. That's our Does that give you your answer? You didn't want to ask that question though, because I went with, yeah, you got to go with math for that, right? But hope that helps a little bit. Okay, how we doing on Bayes? Great. So we continue on where we left off the last time. Okay, I believe we got through this model where we added our predictors, right? And we had to put them in the likelihood. So we made a model for each. Is that correct? Okay. Did we cover the next step, right? Where we had to add um, interactions. I don't think we did we? So let's see how easy it is. Now, Bayes has been hard to this part, right? It's been a lot. But now interactions are going to be where we take a little breather. Remember in maximum likelihood, Enders in this chapter described a few different ways of looking at interactions. The first thing, the just another variable approach, where you multiply things together. Well, it turns out in JAGS, because we sample, these are our two predictors that may or may not have missing data. Because they're in the likelihood function, or they're in the model, that means we have complete data on both of our predictors. We have complete data on both our predictors. When we form our model for either one of our variables, we can create an interaction coefficient by taking each of the predictors and multiplying them together. That's it. Right? Everything's complete when you get to this step of the model right here. So this is our use.cc10x female is our interaction unstandardized coefficient. cc10 obs and female obs are our predictors that have, for their missing data, values imputed. Pretty good, right? I think that sounds good. What do you think? Questions on that? Okay, I like that. Um, now, coming up with a standardized version of this will be harder, so I'm not going to do that. Okay. But similarly, the performance variable will be the same. But again, this is one of the nice things about imputed data is that once it's imputed, sure, once the hard part's over and you have a complete data set, then you use the data set as if it were complete in the first place. You don't have to do anything else otherwise to build it. I like that. What do you think? Any questions on this? No, no questions. You want me to run it? See how it goes? One thing I will note is the posterior density of that interaction parameter, though, will eventually, as n goes to infinity, it will be normal. The posterior distributions converge to normal as sample size goes up, right? However, for finite samples, because it's a product of parameters, a product of not parameters, a product of variables, it may or may not be as normal. The same thing happens in like a mediation analysis, right? Where you may have a mediator and you're looking at kind of an indirect effect, right? Or the indirect effect of one path of an mediation analysis. It's a product of parameters. The parameters may be normal, but the posterior distribution won't be. Here, let's take a look at our autocorrelation and see how it looks. You'll see this time our autocorrelations can be quite high, right? Performance female is 0.63, right? And if I do our plot, of course, figure margin's too large. Oop. There it is. Now our plot starts to look like looks a little bit better. I mean, you see numbers on it, right? Um, but that just indicates that we may not have a long enough chain to summarize what we want. Of course, I have all these plots now. The other thing I will show is the model output. All right, here in the model output, um, the variable I'm looking for is performance CC10 by female. And what you see here is its interaction term for the performance variable is 0.75. Let me ask you this. Is that interact if you were doing this as a frequent, if you were trying to see is this different from zero? I wouldn't say, well, I'll say statistically it's different. Let's pretend we're frequentists playing the Bayes game here. Would you call that a significant interaction? How would you know? Well, let's take a look. Let's do a nine. Let's even go a step further, where you're 95% confident. Let's look at the 95% confidence winter, credible interval on this. Negative 0.043 is the lower bound. 0.19 is the upper bound. So because zero is between those numbers, I'd say the opposite, right? It's plausible that zero happens to be the value of this interaction. How's that for interpretation? The other parameters, by the way, the other interpretation would still stay the same, right? So this perf CC10 variable is now, how do you interpret it? Here we go. Lisa's listening. I'm going to record this. No, I'm just kidding. They're all laughing. If you've had Lisa Hoffman, you'll know why I'm saying this. She is the queen of interactions, dare I say? Not the only person that is, but they're very important to her work. So she interprets interactions very well. What is this? How would you interpret this slope right here? Yes, correct. It's a conditional main effect, or a simple main effect, as she would say, which means you're interacting. This is the slope when the interacting variable is equal to zero, right? What would the slope be? So in this case, female being zero means a man, right? What would the female slope? Sorry, yes. What would the female slope be for CC10? What would you need to do? See smiles. You want to try? Add them together. Yes, right? You want to go down to the, the regression line. You can kind of see what the quantities are, right? You say, hey, I have beta 1 times CC10 and beta 2 times CC10 times female, right? So when female is 1, that goes away. These two, we can do some combine like terms, beta 1 plus beta 2 times CC10, right? And this would be called sometimes, although it's just, in this case, it's a categorical predictor. If this were continuous, sometimes we call this a simple slopes analysis. Remember that term before? So how would you create a posterior distribution for that? Anybody do it the hard way or the easy way? I'm going to go the easy and lazy way. All right. I'm going to add them together in JAGS and have it calculate my posterior distribution. How's that sound? All right. I'll call this perf CC10F. Here we just simply put the two parameters together as if we were adding them into a new variable. We do need to keep track of this, so we have to tell JAGS here to keep track of that model parameter. But if I rerun this, then what do I get? I can go up here and find my slope for female right here is 1.26. How's that? So is that significant if we call it in the Bayesian sense? Well, how would we tell? Is zero within our credible interval? I look at the 95% credible interval. It is not. So this implies that there is a significant relationship for females between CC10 and performance, but not for males, which would indicate that this interaction was significant, but it was not. So this is the weird part about Bayes with that part. But the point I'm trying to make here is trying to add a little more value to your Bayes. If you want a posterior distribution of any linear combination of your parameters, it's fairly easy to compute. The other way I was mentioning would be to go into this object itself, right? And here we go. Another on the fly example. I should just quit doing this, but let's see if I can get this one right. Practice makes perfect, right? So if I take my Sims matrix, oops. I like how it's called Sims matrix. It makes me think like Sim City or something like that, right? All right, here perf cc10 is one of the variables. Let's see if this will grab it. Yes, there it is. And I want to add to that perf cc10 times female, which should be another variable. So if I say perf cc10f equals that, oops, try that again. So now perf cc10 is a Markov chain of the sum of the values from every iteration. And if I wanted to describe it, I could take Copilot knows nothing about what I'm doing. Of course. There we go. That is the posterior density of our simple slope as well. So the two ways you can do this is number one, directly in the JAGS algorithm. Well, JAGS will do it for you. Or number two, you're like, oh, wait, I had 50,000 of these to calculate. I'll go and take the output of the result and play with it. But both should give you the same answer. Although I will say, me rerunning the algorithm will change the random seed a bit, and that may change the results slightly if I for a shorter chain. Okay, how we doing? We covered yes, Farhan. Yeah, that's it. That's it. Right. So if you think about your study plan, if you're let me put this a little bit better. If you're collecting real data, you usually have an analysis plan in mind, right? In that analysis plan, you like to go and specify, I need to understand this effect or this effect or that. That's the ideal. If you have that plan, you can build your JAGS code and then check off every line of that plan with the effects you need by building them. Just like you would, like if you're doing this in R and you used GLM or LS, excuse me, LS, um, LM, excuse me, the LM function for a linear model, there's a package that we teach from GLHT, general linear hypothesis testing, which you can calculate all the simple slopes and effects, one parameter or multiple parameters. So that this is parallel to that as well. Now, in practice, though, I don't know about you, my analysis plans seem pretty good until I hit the data, and then I always forget parameters. And that's where, if you don't want to rerun your analysis, if your analysis takes hours, which some of yours might, then you can always take the posterior distribution and form those parameters in the same way and look at their density from there. Did that answer your question? All right. I think I've got another hour left. How about we take a break here for 10 minutes and then come back and I will finish this example, talk about the Albert and Chib paper for Bayesian with missing data on categorical data distributions, and then talk about homework. Okay. See you in 10 minutes. 1:30. All right. Let's move on to our next model. The next model that we're trying to recreate is this model from this example where, again, our core model that we're interested in is simply this perf and use right here, right? Perf and use being predicted by female in CC10. However, we have auxiliary variables. So what we did in this analysis is we put the auxiliary variables into the analysis. We correlated them with both female and CC10, and we correlated them with both performance and usefulness, right? And so what we end up doing is we end up having this crazy looking joint distribution that involves all of the auxiliary variables. We note that the auxiliary variable for female is not being treated appropriately, and this is being treated as a continuous distribution. But the rest of it seems to be pretty straightforward. Remember last time, or not last time, the time we ran this, some of this, all of this other stuff was a lot of code, but you didn't have to change how you looked at your regression. Hey, I'm going to look at my regression parameters and build those into a model. Not even build a model, I can just take the output, interpret it. This is where the JAGS idea starts to break down, because what we can do, now we can put all these auxiliary variables in a model, right? We started last time up here. Get to it. I have it in my, I have a couple comments here. Remember, this is sort of how we designed our analysis. We basically said, okay, what we're after is this joint distribution of all the variables in our analysis, and we're breaking it down into a distribution for perf conditional on these, and a distribution for usefulness conditional on these, and then actually it was this right here. This was the non-Bayes, this was the Bayesian analysis, excuse me. Female by CC10, actually that one isn't in our analysis. This is the sort of the analysis we built, right? Does that make sense? Sort of this factored regression approach. I've been sort of playing around with this. In hindsight, I think that this is a good roadmap for how we build things, right? We have to come about with this distribution. We know that this is a linear regression, this is a linear regression, and so forth. So that's how we're building it. And actually, this term, this is what it is here. Okay. So in JAGS, it's not as easy to take this Lavon model and build it, because the auxiliary variables may or may not have missing data. So number one, we can't put them into a multivariate normal distribution, right? Number two, the distribution that we may have been able to build with the auxiliary variables, but with correlating with the other parameters or the other variables, is also not possible, because that's a multivariate normal distribution. So instead, we have to build a massive model of factorized regression for each of our model variables into JAGS. Then the output, though, is not going to be consistent with our output from Lavon. And you're going to see why in just a minute, because for us to include all those terms, we basically have to include extra predictors in our regression line. The extra predictors in our regression line, our regression model parameterization, now make that model conditional on those variables. So yes, we're using it there to modify it for missing data, but the model itself now, we have to do extra work to go and get it back to where we would be able to describe it. So I'm going to show you how to fit this. I'm not going to show you how to unparameterize it the right way, because I don't think you're going to do this. At this point, you'd probably be like, you know what? If this might be the last straw with Bayes. Actually, I know the last straw is probably the first straw for many of you, but let me just show you how to do it for complexity reasons. Leave it there, and then we'll fix this next time with multiple imputation. Okay? Okay. So in no particular order, remember, when we take a joint distribution, we can factor it in multiple ways, right? We could start with one variable with is marginal, or another variable is marginal. It doesn't really make a difference. The model itself should be the same as long as we put everything together. So I started with HSL. HSL is an auxiliary variable. It may or may not have missing data, so I'm going to put it in the likelihood function itself, or put it into the model parameterization. So this step for HSL is exactly what I used for CC10 in the previous step, basically, as an auxiliary or a predictor variable. Okay? Let's move on to MSC. MSC, however, so this right here is basically, this is F of HSL. That's the distribution we would call it. It's unconditional. It's just getting its mean and variance, or precision in this case in JAGS. How's that going so far? Okay. Now for MSC, what you're going to see is MSC, I'm going to take HSL and predict MSC with it. Why am I doing that? So this, by the way, is F of MSC HSL. Why am I doing that? Right here. Nobody knows. Well, what was the distribution of HSL and MSC up here? Right, right there. This was the covariance between HSL and MSC, and coupling that with knowing that Lavon uses a multivariate normal, it basically says this, we were estimating basically a bivariate normal between these two distributions, right? So what this is trying to accommodate is if we take, really what we're after is some joint distribution of HSL and MSC right here. But the way we're doing that is taking the conditional distribution of MSC times given at HSL and multiplying that by the marginal distribution of HSL, right? So this regression coefficient is now taking the place of the covariance in the joint distribution. Does that make sense? Right? And we started the class talking about standardized coefficients before, and I mentioned this thing is in units of outcome per units of predictor, right? And we strip those units off. We could also turn this thing into a covariance if we really wanted to. We could get back to that covariance was estimated. I'm not going to right now, but that's basically it. So the answer to my question is, why is this here? It's here in JAGS because number one, we can't use a multivariate normal for it. And number two, this is an equivalent model parameterization to the multivariate normal. So it's the same model as if we could use the multivariate normal, but it's parameterized slightly different. Does that make sense? Right. So we're still estimating for these two variables a joint distribution between them. Okay? So we go on. It's funny. I asked the question. I see some of your looks, and I'm like, I know the answer is no, but I'm going to have to go on, right? You realize that? Yeah. Excuse me. This joint distribution. So what we're after is a model that we need a joint distribution for these variables if they're auxiliary, but JAGS will not let us do that. So an equivalent model formulation is what Enders is calling a factored regression. Right? We take this and factorize the joint distribution into basically a regression model times a marginal distribution. Right? Does that answer your question? There is, again, in JAGS, it will not do multivariate normal with missing data. So previously in Lavon, the pair of these variables followed a multivariate or bivariate normal. Yes. Yes. That's right. That's right. That's right. Well, there's another thing. I mean, remember in the bivariate normal from Lavon, we would have had a mean for HSL, a mean for MSC. Here we have the mean for HSL, but we actually don't have the mean for MSC. It's a conditional mean we have down here, right? So what it's done is taken the parameters. There would have been five parameters with this joint distribution, right? Two means, two variances, one covariance. We still have those five parameters, but they're not in the same metric anymore, right? We have a mean, a precision or variance. We have another mean, another precision, and we have a term that stands in as a slope that would be the covariance. So that's what's building our pieces of our previous joint distribution and putting them together. Does that answer the question there? That's right. That's right. So we can, if we wanted to get the expected value of MSC by itself, it'd be this thing, right? Plus this thing times the expected value of HSL, which is its mean. We could go and calculate it if we wanted to. If we wanted the variance of MSC by itself, we could do what I did at the beginning, where we take this thing squared times the variance of HSL. We could get those parameters back with some transformation of our model, but that process, particularly once we get to the full model, is going to be very tedious, right? How are we doing? Does that work for you, Farhan? Okay. How's everybody else feeling about this? So guess where I'm going next? What am I going to do to MAS? By the way, what I'm doing in this example is foreshadowing chained equations in mice next week. So this process of breaking down, it's not exactly, it's sort of slowly building it. When we get to multiple imputation with chained equation next week, this is going to look very similar. So here, GitHub Copilot is showing you what I was going to do. And it was right this time. Ooh, 20% accuracy. So now I bring MAS in. And what am I after here? I'm actually after this next step would look like this. Like that, right? So to do that, MAS has a predictor of HSL and a predictor of MSC as well. So now I have yet another. These are all auxiliary variables. I don't care necessarily what these coefficients are. I care that they're in the model jointly together because any missing data on any of these will help better be informed by imputation. I think that's the more important thing to realize here. How we doing? Okay. So MSE does the same thing. Right? All those become predictors. And then I get to female. And female, though, is binary, a binary variable. Well, I can still use the Bernoulli distribution for it. But now, instead of just estimating proportion, now I'm going to make this a logistic regression. Right? The logistic regression, this iLogit function takes everything in the middle and converts it from a logit to a probability. So this is a conditional probability right here. And dburn right there is the subject of many jokes just because dburn is the name. It's kind of funny. But other than that, it is the Bernoulli distribution function. So here, this female variable is f of female, given all the others, HSL, and there we go, right there. Right. So now female is not an auxiliary variable. It was part of our model that we wanted. But what this is going to do, you can see, is when JAGS imputes female, it's going to use this entire function to impute it. So instead of imputing female with just a marginal probability, hey, there were 60% female in the class, each time I go through the chain, there's a 60% chance a person's a female. Now it's going to have a much more intricate set of probabilities to impute female with. And that's where female gets filled in. Okay? You can see the benefit of it, right? The more variables we put in, potentially, the better the prediction of that score should be. All right, same thing for CC10. It's given female. Oh, look at that. I didn't actually code this correctly. I left the female slope off, didn't I? That's not good. All right. There. So now CC10 is conditional on all the other variables. We're getting close. Can you guess what I'm going to do for the model for use now? It's conditional on everything before it as well. Now, this is where it gets crazy. I'm not interested in the relationship between HSL and use. HSL is a auxiliary variable, but because I've specified it in my regression line, my regression model for it, that means now all these other parameters are conditional with it in the model. So I'm not able to remove it. And honestly, the code to go and unremove it would take quite some doing. So I'm not even going to show it to you, but I'm giving you the concept here. Okay? This is this is actually kind of the nature of methodological research, right? We have ideas of what the right solution should be. We don't have software that gives it to us yet, right? So those of you who follow the path like I have and tried to learn as many methods as possible, this is part of an example of why methodological research exists, because we can be like, hey, I can fix this. I just need a better version of software to do it. And you would have to build. I can't build anything anymore, it seems like. Now, I will note I added the interaction term here as well. So obs and female are there. But again, these parameters are not the same as what we saw in Lavon, because this is now conditional on a whole bunch of other variables. Okay? Okay. Can you guess what we're going to do for performance now? Same thing. There's all the variables. Now, I will say one other note. There was one parameter I left out way back when we first introduced the model, and I didn't want to introduce it to now. But in our JAGS model, not JAGS, in our Lavon model here, performance and use were endogenous variables, and we estimated the residual covariance between them. And the way we could do that is if these two variables followed a bivariate normal distribution, this covariance would just have a spot in the covariance matrix, that 2 by 2 covariance matrix, right? We don't have that in JAGS. So given the code that I've just shown you here, how would you parameterize this right here to include a parameter that's not equivalent to, but serves the role of the residual covariance? Would it have to be a covariance or a slope? Let me ask you that. Mm-mm. It has to be a slope. Can't do a covariance because we don't have a joint distribution in JAGS available to us. So it'd be this. We take performance and predict it with usefulness. Right here. Then this parameter would get the empirical prior as well. Remember our empirical prior from last time? Each of these regression coefficients has a prior of a normal distribution where the mean of that prior is effectively a parameter we're estimating, right? The mean of the coefficients. And the precision is a parameter we're estimating as well. But if I put this slope in, and I could have done this in the model above as well, I just didn't open that door yet to show it to you. Now, this again is not a residual covariance, but it's taking the place of it. So this model that you see here is fully saturated, has every parameter estimated. And that's what we can use if we need to go and estimate an equivalent model specification in Bayes to what's in MLE. But clearly much more hard to do. So, yes, with missing data. That's right. That's right. If we could just use a multivariate normal in JAGS, we could build the same thing that we had in Laban much more straightforward. But we can't. Right. That, that's right. That's right. Yeah. So what we've done is taken a very big, messy joint distribution, broken it into a series of marginal and conditional distributions. We have the target distribution, the thing that we're after, this full joint distribution of predictors, outcomes, and auxiliary variables is specified the same. But the results will not be meaningful to us because everything's conditional on the other terms. So is that a letdown? Probably. But okay, so there's my Bayes spiel. I could run this. Here, let me just run it real quick. Of course, I may break now, but I'm gonna have to fix that. It is running. Hey, what do you know? I didn't save one of the outcome parameters, one of the slopes, but you'll see that the values of this will not be anywhere equivalent to what's before. One thing I do want to show you, though, is some of these posterior distributions, right, of use and perf 3. But here, we got a lot of parameters. The use parameters here, use CC10 by female, that's a different number. Actually, this is the number I'm looking for here. That 062 is not the true interaction. It's the true interaction when we control for all the other predictors in the model in this case. We'd have to go and do something else, which getting to that something else is very difficult. So, not touching it. Questions? So, benefit of Bayes, number one, we can specify distributions appropriately without like the female variable, right? There's no big deal. Implement it, impute it, it works. Drawback of Bayes, at least using JAGS in this manner, missing data with multivariate normal makes it very difficult to understand. We can at least understand the factorization. That's hard enough. But what these parameters mean and how we go put them back on the same scale is much different. Now, I want to make another point before I end it here about this set of slides. And remember, the third observation of performance and the eighth observation of usefulness, those were missing data. And the posterior distribution here has the mean of the performance for that third person be 12.478, and the mean of usefulness be 60.956. And you have this associated posterior standard errors as well too. If I compared that to, what do you think is going to happen if I compared that to some of our previous models that we've run? Let me see if I can have saved it in each. So here, this was model 3A. The mean of performance was 14 with a standard deviation of 2.7. And now with our auxiliary variables, it's 12 with a standard deviation of 1.93. The point I'm trying to make with you here is you can sort of see the process by which auxiliary variables add to our information about missing data, in that we get what's thought to be a better estimate of what's missing. It's a smaller standard deviation, and that all depends upon our missing data, our auxiliary variables relationship with it. Does that make sense? You can see it. I mean, in our code, the nice thing, one thing I will say, to me at least, teaching wise in Bayes, is this is getting you to think about a multiple imputation and adding basically a model for each one of our variables as we go, because next week we will definitely be using those ideas. But we added more variables. Do you feel more confident that that missing data point should be somewhere where 12 with a standard deviation of 1.93? Do you feel better about that? What are we assuming about that, though? Yeah, that our model is correct. And remember how we specified it, right? We have linear effects everywhere. If there's anywhere non-linearity, like if we have curvilinear, it's probably not going to be accurate. In fact, it may be overconfident, right? The same as idea when we get to next week with multiple imputation will be there too, because it's really easy to use a function called mice from the mice package. It'll give you a ton of data sets quick. And it sounds pretty good. And most people say, yeah, that's good enough, right? But it uses linear effects as well too. And this to me is part of, I do like the structure of the book, how he laid out Bayes after ML and before multiple imputation, because these are issues that aren't going away. We have to be certain that that's correct enough to build, right? The other thing I will note is, um, well, for missing not at random, it's a similar idea, right? In missing not at random, we don't use this kind of general approach to filling in what data are. We have a very specific hypothesis about the missing mechanism to fill in data. And so what we're looking at is a comparison of sort of a standard default approach. sometimes we call this agnostic to a model, even though there's a model behind it. It didn't specify, I use this series of joint and conditional distributions. So this looks like a model, but taken only from this line of code, it's only a logit model. But when you take the entire model together, it's a big joint distribution that we built it, right? Because I didn't specify anything outside of that big joint distribution, we'd call this somewhat agnostic, even though that doesn't look agnostic at all right here. But once you take a step back and look at the joint distribution, we're saying, yeah, it's all joint with the assumption of linearity between the predictors, right? So that's what we have to think about as we get to missing not at random is we specify a very specific distribution for our missing data, a very specific regression or so forth. And we're always going to have this problem of default, linearity, fine, assumed, or not. Do we need to be more specific? But how does that sit with you? Yeah. Oh, yeah. Yeah. That's right. Well, here you'd have to go line by model, right? So what you'd have to do is go and plot predicted values of MSC mean by HSL and take a look for that. So really what we have here is not just one regression model. We have, well, this is sort of one, but one, two, three, four, five, six, seven. So yes, we could look at 7 different models for linearity as well too. What's your capacity for multivariate stuff? Because that's really where you're at here. And you can tell, like, to do, like, I don't know about you, but when I get this amount of certainty in my output, I start to get nervous too. But this is a very standard type of analysis that we've sort of mirrored. So that's that. How am I doing? How are you doing? How are you? Questions on this? So Bayes fixes some things, but not everything. Yeah. Yes, that's right. Every value, every model. Now I didn't save it, but you could. Like if I took off the 3 here, I'd have every value of performance saved from every chain, including the ones I've observed. Um, as you might imagine, the object itself gets quite large then. Right? A Markov chain is thousands of values of every parameter. And if you then save every data frame as well with that, it's massive. But yes, you do get all the missing values back. I mean, the imputation. JC. No, I mean, they will be treated just the same as. That's right. That's right. In fact, we probably expect it. If you have missing data on the variables of interest, you got to likely, I mean, practice says most auxiliary variables will have missing data. I've given you examples where they didn't, but most will. And in here, the way we structured it, we'll be fine with that as well too. And then when we get into multiple imputation next week, the same thing will happen. Yes. Yes, that's the hard part. And it's not even a covariance. Like if I wanted to go and get UCC10, UCC10 female, and use female, not conditional on each of these other predictors, that's even harder. Right? There are ways to do it. We could probably do some math and figure out what that is. Honestly, I don't know that anyone will want to do that in code unless you absolutely have to, right? And I'm going to guess that you probably don't absolutely have to. But yes, yes, that's right. Yeah, we have to go and remove. This isn't our focal model anymore, right? This is more than our focal model. And so I don't know off the top of my head how quick you could go back to just our focal model. Like you have to do a lot of different. steps to get back to that. In part because, so if everything were multivariate normal, where are my hedges, right? Multivariate normals are great, right? If we had everything as multivariate normal, like we treated female before, then if we condition on one column of that, we know what the other covariance matrix is, right? There's formulas for that. And we know what a marginal covariance. We can go back and forth, we can build this, we can see it. The problem is we have female as a Bernoulli variable there, and the joint distribution of Bernoulli and multivariate normal is not, well, I don't know what it happens to be. It's not like you can quickly derive that. And so that's a catch that we may not be able to undo for what we have with this specification. Yeah. Yeah, you could, but then it's hard to say. I think you'd have to. One thing you could do, and maybe this is me not, when I get, this is me reaching my limit with Bayes. And you know me, I'm a Bayes guy, right? This is it. But I think what you might be able to do is, no, so you have to marginalize across each of these other variables, right? And so by marginalizing, what does that mean? You have to sort of integrate them out or sum them out. There may be a way that you can take sort of the average of what these parameters should be, but even then, I don't know how to do that. Yeah, I don't know. Vladimir, I don't know the best way forward with it. I'm just going to say that. And I've sort of hit a wall with understanding what that needs to be. My wall is solved by next week, though. All right? Is that better? Okay. Turns out next week, we're going to impute variables. Um, we'll be building maximum likelihood with it, but you could actually turn JAGS into your imputation like analysis machine if you think carefully about it as well too. But I don't know that I'll show that to you because I don't know if anyone does that. But if you don't want to go through the steps of compiling all of your analyses into one big analysis, there could be a way to do JAGS with it. But that's just because you're going to do multiple analyses on complete data. Anyway, yes, Vladimir. Hmm. Hmm. That's exactly it. That's right. We have to. Yes. Well, yeah, I didn't specify it in this model because it gets really difficult to show. But really, what we have here is like for any one model itself in Bayes, a lot of times we specify the likelihood of the data is conditional on, let's say, right here. And so the Bayes solution is to multiply it by the priors for each. So if you specify it out with all the parameters, then you can see where that goes as well too. Yes. Yeah, the whole model itself, it works together at the same time. Yes. Yep. Other questions? Yes. Mhm. No, actually, in the same way. Yeah, there's nothing about, so this specification in MLE works fine too. What, I'm not sure I understand your question. We may have, I don't know. Yeah. Yeah, but well, think of it this way. Think of it this way, right? In our maximum likelihood, we treated all these auxiliary variables as multivariate normal. If we're missing any one of them, it just resized instead of having four, if we had three, it would be a three variable multivariate normal. That's right. That's right. And technically, the Bayes algorithm could work in that way too, but the way that JAGS is programmed, it does not. But yeah, so it would. What I say about auxiliary and missing here is the same for missing with multivariate normal. As long as the auxiliary variables are built into the model likelihood, the multivariate normal will adjust to the size of what's observed versus missing. Yep. Mhm. That's right. Mhm. Oh no, no, that's it. You can never assume anything's going to be complete, right? Those of you who have lots of data, how much of your data are complete? You're missing I think you're missing variables on things that you probably know a lot about, right? So I know a little bit about his data, so I'm thinking, yeah, that's it right there. So when I say that, I only mean that with like only in like if we were in completely theoretical statistics, we'd make an example like that, and it would sort of start us on the theory path. But reality dictates that there is no such thing as complete data. I think that's the way we have to address it, right? What do you think? Yeah, thank you. It's possible, yes. Like you could use JAGS to impute all the data and then output and do an analysis. You could potentially. Is that what you're saying? Yeah, yeah, you could. What we have here with this model in JAGS actually mirrors what mice would give us as well. So, yeah, we could think about it that way. It's sort of a Bayesian version of what mice has with all the specification that we have here. Thanks. Other questions or comments or thoughts? But at least we know a little bit about missing or imputation. All right, shall I spend a bit on categorical variables? The chapter 6 where I'm like, all right, who wants a history lesson? I know. How do you make statistics better? You get history. Yes. And you know what? We can go even further than that. We can add law or accounting. Let's just put it all together, right? No. History lessons this. 1993, June 1993. I don't know about you, but I was quite young at that time. So don't know what was happening in my life. So you know a little bit. I think that was summer of my junior year in high school. That's how old I am. Anyway, this paper by Albert and Shib came out, and it talked about Bayesian analysis of binary and as they called polycotomous response data. In psychometrics, we might call that polytomous data. But this is one of the most important papers to my life that came out. And I just want to mention that for a little bit. It's the basis of chapter 6. But basically, it said this. Imagine you have, now just ignore all this from before. I'll even clear my R console so you don't have to even be trapped by it. I'm only going to describe this in the context of just a simple binary logistic regression. Okay? So, in logistic regression, if we wanted to put prior distributions on our beta parameters, let's imagine our betas are normal. The logistic regression, what's the distribution it assumes of your outcome variable? Let's say binary outcome variable. Bernoulli, I'll just say it. Bernoulli distribution. So you've got a normal prior and a Bernoulli distribution. That combination for data. That combination is not a conjugate prior. Right? Not a conjugate prior doesn't mean a whole lot because we have Metropolis Hastings. But Metropolis Hastings is somewhat inefficient, takes longer to run. What this paper says is I can find a way if I switch my model data from, it's still a Bernoulli distribution, but I switch my link function from logit to probit, then with the approach that they show here, I can show that that is a conjugate prior. A normal is a conjugate prior on a probit regression. Remember what a probit is? The normal ogive, the inverse, so the probability you have gets backwards transformed into like a z-score that you predict. Here's how it works, though. Basically, let's talk about from complete data here, because with incomplete data, it gets a little bit easier. For complete data, what Albert and Shib found was that if you created a continuous variable z that followed a normal distribution that was truncated, and the location where the truncated normal was whether or not somebody had a 0 on the dichotomous or a 1, right? If they had a 1, the truncation part would be lower bound is 0, upper bound is positive infinity. If it were 0, if there's 0 on the dichotomous variable, the truncated normal would be at 0 again, but the upper bound would be 0, the lower bound would be negative infinity. So what this algorithm does is it creates what they call underlying variable, what Enders calls a latent variable. I guess it's a semantic term. It imputes values on this underlying variable following a normal distribution. And then it shows that if you do that, then the distribution of your coefficients is also normal. What that means is when you specify a binary regression with a probit link function and normal distributions on the priors for all your parameters, you can build a Gibbs sampling algorithm to sample your parameters directly, not having to use rejection sampling in Metropolis Hastings. Now, if you were to compare the two approaches, if you were saying, yeah, I'll do this augmented data approach, a lot of times in the stat literature, we call this augmented data more than latent variable. But if you were to do this approach, augmented data, and compare it with Metropolis Hastings without, the results, if you run the chain long enough for both, will be equivalent, roughly similar, right? It's not a model specification difference. This is why I'm looking at chapter 6 and saying it's an efficiency thing. You don't have to do it this way. It's also written, I think, because M plus does it this way. But think of it this way. The trick is this Z value, if we have missing data on Y, right? Y tells us where to truncate the distribution to give us our fake data, right? If Y is missing, we just remove the truncated normal from it and sample it with a regular normal distribution. That's it. And that's chapter 6. And then instead of using Y in our subsequent analyses, like if we want to predict something with Y, like if it's part of a bigger model, like female in our previous model, instead of using Y, we use our filled in data instead. That's it. That's not it. It's really complicated, but it's pretty cool, right? Would you like to see this in action? A long time ago, I found this code online. I can't even find where I got it, but it's from 2007, November 15th, 2007. What a great day. What a great day. It's still in my, well, no, I was 30, but still. All right. Just barely. Um, this is the algorithm right here. You can walk through it. I'll just quickly show it to you. The first part generates data and sets up a few priors. So our data are this. We have our X variable where we just have a intercept and then a predictor. And our Y variable, this is complete data Y, just a bunch of zeros and ones. Okay? You want to see the Gibbs sampling algorithm step by step? I'll do it for one iteration. Okay. How Gibbs sampling works here is it starts, remember we have to have starting values. So we pick values of 0 for beta to start. Could be random, couldn't make a difference. Should be random, but we'll just show it to example. So this right here, if we had, well, this is complete data land. So let me just show you how it works in complete data land. So for this, once we make the linear combination, X beta is our predicted value. So this should be effectively in probits, right? So mu Z is the mean value of this auxiliary variable or this augmented data variable, conditional on X. That's what that is. So now what we do is we can create a Z for every person using a truncated normal. So here, if for everybody who was 0, their truncated value is truncated above at 0 and truncated below by negative infinity. But the value of the mean of that distribution is set by what's predicted in the regression. Right? Similarly, if you were a 1, your truncated normal is the same. The mean is the same. It's just now your truncated normal is positive, not negative. So if we look at Z right here, there's our Z variable right there. That's our truncated or our auxiliary variable, right? And then we can sample our betas from a multivariate normal distribution right here with these values, right? So beta star is, where did it go? Not seeing it here, but these are the values of the parameters. And beta mat here, whoops, I is not found because I should be 1. This right here was basically sampling them. Whoops, right there. So that's sampled values of the beta values. And here, let me show you what beta should be. Beta should be negative 7.75 and positive 0.75. So I'm going to run this Gibbs sampler real quick. That's how quick it ran. You'll note I'm not rejecting anything. I'm sampling Z straight from a posterior distribution. I'm sampling beta straight from its posterior distribution. So there will be a little bit of convergence needs. Um, Here, if you want to see a plot, there is the slope. So you could see I probably need a burn-in period, but it quickly sort of converges. This would be the expected value of it. But now if we took the last 500 trials, you'd see our values were not exactly 0.75 and negative and positive 0.75, but not far off from it either. But that's how it works. So I know we're up on break. Let me finish this in homework and we'll call it a day. Okay? So no break. Is that all good? Good trade? Because otherwise you'll take 10 minutes to come back for 5 probably. So that probably won't work. How are we doing with this so far? Let me tell you, this changed my life. You want another story? So I was sitting and working at Kansas the second time, and I was teaching a Bayes workshop, rediscovered this paper, and I was like, I wonder if I could estimate that with my version of research, which these diagnostic models, these really difficult to estimate IRT-like models. A bunch of binary data, and it turned out I built an algorithm that did, and it works amazingly, right? Uses this approach, data augmentation, and so forth. Well, in the process of doing that, built that algorithm, um, was getting ready to publish it, and a company said, "Wait, we want to incorporate that into what we do for some psychometric stuff." That company was then, so they licensed this algorithm from Kansas that I wrote, and I've been receiving royalties, I'll say, every year. Not only that, my old department has a fund that gets royalties as well that they're using every year. I don't know how much longer this will work. I don't think it's going anywhere. So it's not that big of a deal. But still, money is money. But the other cool thing about it is this thing always works. Like before, I'd have these estimation problems with these models that were pretty common. And now it just flies. So this is a great, if you're in the methods world, for those of you in the class that are like trying to be a little bit more develop these things, learning about this is fundamental. Learn it, read it, understand it, try to code it. Use this code as an example. It's really amazing. Like you can incorporate that. If you have to build your own algorithm, this is a good place to start. Now, that was it. That was my story. Sorry, too much history. Let me show you how this works for missing data then. Okay. So for missing data, our catch is this. If an observation is missing, rather than using a truncated normal, we don't know if they're 0 or 1 for y. We just remove the truncation from it. We sample from a normal distribution where the mean of it is still the mean predicted value on the probit scale. The variance is always 1, and we fill in our data that way. And then with the complete data, then we sample our covariance, or our betas. And so I can show you what that looks like here. And so now ZMAT is not found because I didn't set it. There we go. So ZMAT right here, these are the values of missing data that I imputed for each of those first 10 observations that I made it missing. So if you think about this as a missing data perspective, these will be the imputed values that you're using. Even though you're using an outcome that's discrete, if you stay with these imputed values, it's like you imputed a value for it that would be able to be dichotomized compared to zero, right? So if this were the female variable, this would be like a propensity that a person happens to be a female, right? And in some iterations where it's negative, we would have called them that, female. Actually, positive, negative, it would be male. Positive would be a female. But we don't know for certain. And that's part of the whole system for it. Um, Here, if I make a matrix plot for it, this is the posterior distribution. You can sort of see the different colors. That's each person's Z that was missing. And you can kind of see how they look converged, right? It's a chain. And again, if I were building my own thing that was in JAGS, this might simplify some of the calculations I had in JAGS. Because if Z is normally distributed, that gets me back into the ballpark where everything's multivariate normal with Z instead of female. And maybe I could go and modify JAGS a way to build it better. Or maybe I could go and forget JAGS and build my own Metropolis Hastings for a multivariate model, which takes a lot more practice. So chapter 6 does this for binary data, for ordered categorical data, and actually I do have an example file for that too, the cumulative probit right here, same idea. And then I think it also includes a nominal, like or generalized logit as well too. But again, if you follow what we did in JAGS, none of that matters. Like, you don't need to worry about that necessarily. It's only if you're trying to me, find an efficient algorithm, or this is sort of another tool in the toolbox for how to analyze data that might potentially help you at some point. I don't know when that point might be. But again, maybe make an algorithm with it, sell it to a company. By the way, that company that I sold it to, it's actually the people that make Icon now. So in structure. So yeah, I will had some money from Instructure through Kansas, so forth. Anyway, good story, right? There's your motivation. Go build algorithms. There you have it. Okay, any questions on any of this? No. There's chapter 6. Done. If you didn't read it, I don't think you're going to miss much. Yes. 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 It's just hard. Factor regression actually is what runs multiple imputation also, right? So factor regression is sort of the concept that underlies everything. We will use it for how we disentangle joint distributions, how we build joint distributions when we don't know what the form should be of the parameterization, or how we need to specify things in programs that only work with marginal or conditional distributions, univariate distributions. So yes, hope that helps a little bit. It's a big concept. I wanted to pull up homework. That's why I'm going to our icon site. Yes, I should, disclose a conflict of interest with Instructure. Actually, all the people, that company got bought by Instructure, then Instructure's been bought twice since then. So I don't know anybody since then. The tech world. I will say I did travel out to Salt Lake City a few times, and like, you ever watched the movie or that TV show Silicon Valley on HBO? It's like living in that show. It's like, you go, I'm here at Iowa. This is not that much different from all the other campuses I've worked at. It's a university, right? Built to teach, built to do whatever we're doing. You go into the office there, and they've got like a miniature golf course. They have a full kitchen downstairs. Every floor has a kitchenette with like stock food, so you don't have to bring your lunch. You don't have to bring anything. It's like, wow. And then you get this picturesque view of the valley below. Like, oh, that's pretty nice. Pretty nice. And then other year, you go through acquisitions and mergers and stuff like that. It's like, maybe not so nice. Maybe we just like not having the kitchenette. But yeah, I think I got hit with like a foam ball in one of the meetings. It was just how it works. Um, Different world. That's all I got to say. Let's go with assignment 4 here. Homework number 4. Again, what I'm asking you to do, I thought I took this off and I didn't. I will fix this. I'm asking you to take the final model from homework 3 and specify it with, re-estimate it, take that from before, copy and paste, but then it's all in one document. That's all. And then try to turn that model into JAGS, right? I would tell you that the same approach I took before. Remember, we have MSGPA as auxiliary, we have test score, HS grad, and we have these other variables, parent ed, extracurricular hours, and absences, right? All of those are continuous. So you don't have to switch to the Bernoulli distribution, but I would recommend you start with the same process, right? Pick one of the variables or take the auxiliary variable, put a model for it in first, and then go successively with each of the others, right? I'm not asking you to do a lot of interpretation, right? Just report the posterior means and medians. And I did have you go and give me standardized regression coefficients, so we can do that potentially. That one may be the hardest, but it's also only worth 5 points. So if you omit that, plus you get to drop a homework. So if you don't want to do Bayes at all, save it for the next time. I'm trying to help you here. All right, I'm trying to help you. I want you to learn, but I also realize that this is quite a burden in doing as well. So what I would say is JAGS is temperamental to work with. If you haven't done it before, try to just get an empty model working with MSGPA to start, and then build one step, try and make it run. Build one step, try and make it run. If it doesn't run, send me your syntax. It'd be great if you attach the data and syntax in the same email that I can drop them both in downloads and play around with it. I'm anticipating you working with me building this. Okay? Okay. You're not alone. You have each other too, but I'm going to welcome. It's my job to be the instructor. So anything you can uh, send to me, I'll take. Questions? Yes. That's it. Yeah. The question then would be, what is a model? Because some would say if you bring it into the likelihood, there's a model for it already. And I don't know, that's probably too philosophical. But yes, I put a more precise way would be in JAGS, we specify univariate distributions. And when we pull them together, they're equivalent to a joint distribution. Whereas in Lavon, we have joint distributions we can work with. That is how I would frame it. I think from why I say not a model versus model is if anything has a likelihood, in many ways, there's no difference between that and a model, right? If you think about I don't even have it open anymore. Our JAGS code, a very simple JAGS, the beginning JAGS code, right? Um, use here has a likelihood. It has a model, right? It has a parameter. It's just a mean and the variance. So that's a model, right? We're specifying a distribution. We're specifying the parameters. We're estimating them. It just happens to be an empty model. So is that a model? Is it not? It's a model without predictors. So that's where I was going with um, JAGS and Lavon. Both are models, but JAGS has only univariate distributions you can work with, which some of which can be conditional, whereas Lavon can be joint distributions. Is that better? Yes. In other words, yes. Right. Yeah, partially factored would be leaving some of the factorization out. Um, I don't want you trying, I think you can do the whole thing not partially factored in your homework. Where I would say partially factored shows up, like in this example here, I was trying to mirror the model right here. And this model has a covariance between performance and usefulness. My JAX model does not. And because of that, I'd say it's sort of a partial specification. It's not equivalent to the full model, right? So that's where I would define that as. Does that help? Okay. Other questions? Want some time back? We stop today at 2:30. Okay. Stop today. Check out next week. I will have a chapter 7 lecture for next week. Please take a look at chapter 7. I think that will be the most practical chapter in the book. So we're there. Hope to see you next week. Thank you for being here. It is a pleasure being your instructor, even if the material is kind of hard. So take care.